This is CS50. I'm David Malin, and you can tell because I'm wearing all black. So when I'm not being David Malin, I'm Benedict Brown. I'm a lecturer here in the computer science department, and it's really my pleasure to welcome you all to CS50 at Yale. And we've been doing this. This is now our 4th year, and was great the first year, and it's been getting better and better every year since. So I'm really thrilled to be here. This is my 2nd year with it, and we're looking forward to a fantastic year. You will see me throughout the semester, sometimes in the lab for office hours, sometimes when you come see me in my office for office hours, which I encourage you all to do. I also work a lot behind the scenes with the organization of the class, with the staff and supporting the staff, making sure that they're in a position to help you and work with you in sections and in office hours. And the other person who's really working overtime all semester long on the course here at Yale is Natalie Mello, who I would like to bring up to introduce herself, and then she'll also introduce you to many of our course staff that are here. And Harvard's David Malin will also be making an appearance, I believe.
Hi, everyone. Hi, everyone. Welcome. Happy Thursday. Woohoo! I'm Natalie Mello. I'm the course manager for CS50 at Yale. You'll see me a lot at office hours. I also have, I might have my own office hours by appointment this semester, but you'll see me around quite a bit. So when you see me, I hope you smile. But I'd like to introduce my amazing staff members. So come on up. Woohoo! So we have a full team out here ready to help you out, help you learn computer science. People from all different backgrounds, some not even majoring in computer science. They only took CS50 and they still wanted to help out. So feel free, if you see any of them around campus, say hi, wave to them. If they see you and they remember your face, they'll obviously wave to you as well. So yeah, let's give a round of applause to our staff. And now I'd like to hand it off to Professor Malin.
Thanks, guys. Okay. Thanks. Thanks. All right. So this is indeed CS50, an introduction to the intellectual enterprises of computer science and the art of programming. And what's perhaps striking is that so many of the folks who just stepped up here alongside Natalie and Benedict were exactly where you are seated here just last year. And so let's get one detail out of the way. 68% of you have never, if last year's any indication, studied computer science before. So if you're in this classroom right now and you're feeling, I'm not so much a computer person, or why am I shopping this class, odds are the person to the left of you and maybe even to the right of you is feeling that exact same thing. And if I can say, back in my day when I first got to college, even I shied away from computer science. Even though it's kind of in vogue these days, certainly I dare say it's still a field to beware, and courses like this and others are a bit daunting. I think if you don't think of yourself as a computer person, and you certainly use computers and mobile phones and all that every day, but you don't really know what's going on, and God forbid something goes wrong, it's not really in your wheelhouse to fix. And so ultimately in this class, it's about building comfort and confidence, skills, and a foundation in computer science, and we'll see what that looks like today. And let me start with this message that you'll see in the course's syllabus as well, that what ultimately matters in this course truly is just this, is where, not so much where you end up relative to your classmates, but where you, in week 11, end up relative to yourself in week 0. As we'll soon see, computer scientists and programmers tend to start counting from 0. It's about a 12-week semester. And so by week 11, the 12th, will you hopefully feel quite the delta versus where you feel today. So what is then computer science, and what are we going to get out of this? So I dare say we could distill it, maybe oversimplify it, as just this: inputs and outputs, right? It is problem solving but using computation, using computers, using hardware, using thought to actually solve those problems. And to solve problems, we take inputs. Now, what might the inputs to a problem be? I might want to take attendance and start counting. So the people in this room are the inputs, and the output is the total number of people. Or you have some ingredients in the kitchen, and the goal is to produce dinner, and so your inputs are those ingredients, and the output, of course, is dinner. So that's really what problem solving is, and inside of this so-called black box is where computer science really fits, and giving you the tools and the ideas with which you can take inputs and produce outputs that are of interest to you. But to do that, we have to represent inputs and outputs in some way, right? I'm using English words right now, and if you're taking math classes, you're probably using math symbols and numbers. If you're taking chemistry classes, you might have yet other symbols to play with as well. But so we have to represent inputs in this class and in this world of computer science in some way. So how might I represent information? If I'm doing something like attendance, 1, 2, 3, it's not uncommon to do something old school like 1, 2, 3, 4, and then we have little tricks just to make it a little more compact, 5, 6, 7, 8, 9, 10. So we can just use hash marks. And I could do that on my hands too, not for the whole class, but how high can I count with just one hand? You say 5, right? 1, 2, 3, 4, 5. Not really a trick question, but I dare say I can actually count higher than that on this hand. Right? I'm pretty naively just treating each of my fingers at the moment like hash marks on the board. They're just straight lines representing people in this room. But I'm not really permuting them or combining my fingers in any interesting ways. They're just down or up, but from left to right, or from right to left in your case. So how might I be more clever? Well, what if this is just 0? And what if this is 1? And what if this is 2? So just one finger up still. So not 1, but 2. What if this is 3? What if this, offensively, is 4? What if this is 5, 5, and 6, and 7? In other words, if I actually take into account the ordering in which I have my fingers up, I can actually count up notably higher. Off the top of one's head, anyone want to ballpark how high I can count on one hand? 31 actually, and we'll come back to why that is before long, but 31, that's pretty painful to even imagine or physically do, but if you do kind of permute your fingers up and down in different patterns, we can do even better than just 5 people on one hand. So it turns out that computers aren't all that dissimilar to how they represent information, because we in our human world tend to use numbers like 1 and 2 and 3, and we immediately see that and think probably 123. But why is that? All you see on the screen technically are just like 3 symbols, right? They might be typed, they might be drawn or painted, but these are 3 symbols or glyphs, if you will, that just have like meaning that we humans ascribe to them. And we know that that is 123 because it's been ingrained in us. But we know this because we have had a pattern of, we've had an alphabet for quite some time that's actually pretty expressive, right? I grew up knowing zeros and ones and 2, 3, 4, 5, 6, 7, 8, 9, technically called the decimal system. Dec meaning 10 because there's 10 digits in this alphabet, so to speak, for representing numbers. But it turns out computers are more simple than this, and they actually don't have access necessarily to all of these numbers. They actually, anyone know what the alphabet they actually do use? Yeah, zeros and ones, otherwise known as binary, bi implying 2, because it has just 2 digits at its disposal, 0 and 1. But how in the world, using just 0 and 1, can you count to 2, let alone 3 or 4 or 31 or much higher than that? Well, it turns out it's actually pretty familiar. If you think back to grade school, how you might have first learned math, odds are if you're like me that you saw a number like 123, and it is 123 and not just 1, 2, 3, because this was the so-called ones place, this was the so-called tens place, this was the so-called hundreds place, and then none of us do this anymore, but this would be 100 times 1 plus 10 times 2 plus 1 times 3, and that of course is 100 plus 20 plus 3, and then we get mathematically 123. And even though it's obviously the same pattern of symbols, it now has some mathematical meaning because we ascribe meaning to these columns. Well, it turns out computers work in fundamentally the same way, but they just don't have 2s and 3s and 4s and 9s. They just have 0s and 1s. So they have to be a little more clever how they use those 0s and 1s, those binary digits or bits. Binary digits is where the word bits comes from. And so they just change what these columns mean. And so instead of having 1, 10, and 100, which it turns out are powers of 10, it's technically 10 to the 0, which gives you 1. 10 to the 1 gives you 10. 10 to the 2 gives you 100, and then 1,000 and 10,000 and so forth. Computers actually use powers of not 10, but you might guess 2s, because they only have 2 digits in their alphabet. So this is the 1's place, and this would be the 2's place, and this would be the 4's place, for instance. And now I only have 0s and 1s at my disposal. So how do I represent the number we humans know as the number 0? Well, if I need to put a number in these columns, I'm just going to put a 0. Or, without fundamentally changing the meaning, I could actually do 3 zeros. But just as in the human world, we don't need necessarily all of those leftmost zeros. We just need the 1. How do I represent 1 in binary using just 0s and 1s if I have 3 of them at my disposal? 0, 0, 1. Why? Well, I need 0 4s, 0 2s, but I do need 1 1 to represent the number 1. And here now, can you see why my fingers went up in the order they did? How do I represent the number 2 in binary? With what pattern? Yeah, 0, 1, 0. And again, if that's not obvious, that's fine. You can just literally do the math. Well, I don't need a 4 to represent the number 2. I do need a 2. But once I have a 2, I don't need any more numbers, so I can have 0 1s. So here's where we began. This was 0, all fingers down. This was 1. This was 2. And 3 is going to be what on the board now? 0, 1, 1. I just need to go from 2 to 3. And then when I almost made a gesture, that was because my middle finger could have been up and my other 2 fingers were down. And if we continue this story, how high can you count with 3 bits, or equivalently 3 fingers? What's the biggest decimal number you can represent? 7, because if you just put a 1 in each of these columns, that gives me a 4 plus a 2 plus a 1, which gives me the number we humans know as 7. So that's it. Like all this talk for all these years that you might glean that computers only speak binary or 0s and 1s, it's still fundamentally the same thing that we all learned in grade school and now just take for granted. It's just computers only have 0s and 1s at their disposal, but they treat them a little bit differently. And what's nice is that we're doing this in chalk and we're doing this in fingers, but there's a very nice mapping between 0s and 1s to the physical world. All of us who have phones that need to be charged at night, or all of us that have laptops that are plugged in now or at night or in class, are plugging them into the wall. And even if you're not an electrical engineer, you probably generally know that there's like electrons flowing in and out of things to charge things up. So there's some kind of input, a physical or electronic input that's either there and plugged in, or it's not. And we can actually simulate this with lights. The lights are all on right now. So I dare say this room, SSS 114, represents a 1. It's just on. But if I go ahead and hit a button, which in the real world is sometimes literally labeled 0, if you've ever noticed, now it's off. This room is representing a 0. So this is kind of a dramatic way of representing 0s and 1s with all of these lights. But we can do it on a simpler form. Like all of us have phones, and those phones have probably built into software little flashlights these days. So if I just tap this button, my phone here is now representing arguably the number 1. And if I turn it off, it's representing 0. So using one phone or one flash, or really one switch that I'm throwing digitally by touching it, I can turn a light bulb on and off, or represent a 1 or a 0. And does anyone, can I borrow someone's phone? Or that has, yeah, OK, you don't have to unlock it for me, though. So if I go ahead now, and now I have 2 bits, 2 phones, or 2 switches at my disposal, what am I representing? I think 0, 0. The light bulbs aren't off. If I go ahead and turn on this one, what am I now representing? 1, and now 3. Good. And now if I turn this one off, 2. So thank you so much for volunteering. And so if now I just had more switches, and in turn more light bulbs, I could keep counting higher and higher. So what's actually inside of a computer? It's just many, many, billions even of tiny little switches these days. And those switches happen to be called transistors. So if you've ever heard that word, it's just like a light switch, or the switch on a light bulb that either is turning something on or turning something off. And as soon as you have that ability to turn something on like a 1 or turn something off like a 0, you can clearly count as high as you want, so long as you have more and more of those switches. I have just 3, or I have just 5, but we can certainly throw hardware at it by adding more and more. So let me pause there for just a second, because that was a bit of a mouthful. Are there any questions on what we've now defined as binary? And recall that the reason we got into the weeds here was we need a way to represent information, inputs, so we just need some kind of pattern or symbology. All right, so that's all fine and good that we can represent numbers, but what would you also like that your computer do? Back in the day, a computer was, by definition, really just a calculator doing mathematical things. But of course, these days we use computers and phones for so much more. What might you also want to represent? Well, what about just English messages, or any language for that matter? In English, I might want to represent the letter A. Well, if we have been focusing on math and numbers here and patterns, how do we make this leap conceptually now to represent letters? So you can send text messages and emails and write essays and the like. How might we solve this problem? Because again, the only physical input is like my power cord into the wall. Yeah?
A is the first letter of the alphabet. Represent this one.
Yeah, so that's pretty good intuition. A is the first letter of the English alphabet, so why don't we just start numbering those letters? So if A is 1, sure, and capital A is 1, capital B presumably would be 2, and C would be 3, and so forth. And that's actually spot on. That's exactly what computers do. They actually give themselves a little bit of breathing room, so it's not actually starting at 1. Actually, weirdly, starts at 65. But then the answer is exactly the same. B is 66, C is 67, and so forth. And so just some years ago, decades ago, a bunch of humans in a room essentially needed to decide that, hey, everyone, can we all agree that capital A shall be represented in a computer as 65? Now, in turn, 65 is represented how? Well, as a pattern of zeros and ones, but that's fine. We don't need to keep talking about zeros and ones if we can just kind of talk at a higher level, like our familiar decimal numbers. So C is going to be 67, and D is going to be 68, and so forth. And then there's a whole mapping, so to speak, between lowercase letters and numbers as well. What they are doesn't really matter. Just that there is an agreed upon standard is actually what's important here. So it turns out this standard, this mapping that humans came up with, was just called ASCII, American Standard Code for Information Interchange. Not interesting what it stands for, but we all agreed some time ago. But it turns out that ASCII actually has some limitations. It has some limitations in that you can only express so many letters. Here, for instance, is a summary of just some of the letters we might represent. And just to hammer this home, if this is the mapping as you were proposed here, albeit starting at 65, and you received on a computer somehow some series of bits, zeros and ones somehow, through Wi-Fi or Ethernet or whatever, and the bits you received represent the decimal number 72, 73, and then 33, what message did you just receive from someone on the internet? 72, 73, 33. Yeah. Hi. So 72 is H, 73 is I. 33, it's actually not on the board. Anyone want to guess what it is? It is so well said. It is an exclamation point. So hi is indeed correct. And that's because we just agreed some time ago to have that mapping. So 72, 73 is hi, followed by, if you actually looked at what the dot, dot, dot meant in like an online reference, you would see that indeed it represents an exclamation point. Meanwhile, though, underneath the hood, so to speak, like actually in the computer's memory, and more on memory in the weeks to come, and some pattern of switches, effectively, is actually storing that pattern of zeros and ones. There's a bunch of light bulbs on, there's a bunch of light bulbs off, and they're in groups. And it turns out that computers usually use groups of 8, because it's convenient for today's purposes. 8 bits, 8 zeros or ones. You don't have to write all of them if the leading things to the left are zeros, so we don't bother typically. But computers typically use 8 bits. So if you were to represent in ASCII any letter of the alphabet, you would have 1, 2, 3, 4, 5, 6, 7 bits historically. But it turns out, for convenience, it's often represented as 8. And there's something called extended ASCII. But the point is it's finite. There's only a fixed number of bits, or zeros or ones, used to represent every letter of the alphabet. So what's the implication of that? If you're only using 8 bits, and we don't have to get too into the weeds of math or arithmetic, but if you only have 8 bits or 8 fingers, how many different combinations of fingers up and down can you come up with? 200, well, total patterns, 256. And why is that? Well, if each of these sort of hangman placeholders is either a 0 or a 1, there's 2 options here, times 2 more options here, times 2, times 2, times 2. And if you just multiply out 2 by itself 8 times, you actually do get 256. So with just 8 bits, you can count from 0 all the way up to 255 if, again, you start counting at 0. So it's finite. It sounds like a lot, though. But if you consider a typical keyboard, say a US keyboard, you'll notice that there's actually a lot of symbols not on our American keyboards, at least. And indeed, if you're from abroad or you speak another language and you have a different type of Mac or PC keyboard, there's probably symbols you use every day with family or friends that just aren't on the keyboards that you might see in the computer lab or on most Americans' keys. And indeed, ASCII was pretty biased. Like American Standard Code for Information Interchange, hey, the operative word there was American. And so what apparently can we not represent with a typical keyboard, let alone ASCII? What kind of symbols? If you speak other languages, yeah?
A Chinese character.
Yeah, like a Chinese character, which is not obvious certainly on this type of keyboard. Yeah?
Upside down question mark.
Upside down question mark that you might use in Spanish, for instance, or another language. Yeah? What's that? Accents on A's and E's and values, vowels and other characters as well. So we're just scratching the surface, right? There's a lot of characters you might see in your own life or in any language you've studied that just don't fit that model. So just instinctively then, what is the solution? There's a problem. ASCII is not expressive enough, so what's the solution to representing accents and other characters? Yeah, use more bits, right? And computer scientists might say throw hardware at the problem. And it's kind of true, literally, like just use more light bulbs, use more switches, use more memory. But indeed, that's the solution. So along came something called Unicode some years ago, whereby you can actually use not just 1 byte or 8 bits. So 8 bits is a byte, just a convenient term to describe 8 bits like the ones on the board. And with Unicode, a successor to ASCII, can you use 1 or 2 or 3 or 4 bytes? And no one pointed this out, but I just flew past this. Besides being able to represent things like accents on a keyboard, turns out that these are very much in vogue these days, right? Most of us in this room probably use emojis, perhaps use them a little too much. But what is it? You're actually not sending images per se. Well, you might be. If you're downloading GIFs or animations or whatnot, those might be proper images. But if you're just sending emojis from the built-in Android or iOS or Mac or PC keyboards, you're actually sending a keyboard signal, so to speak. It's not just 8 bits. It's more, because on my American keyboard, I don't typically see keys labeled with all of these faces. But Unicode increases exponentially just how many symbols, accents, and upside down question marks and other punctuation. And it turns out these fun things like emoji that you can actually represent inside of a computer. As an aside, if you've ever seen or you will eventually see the expression UTF-8, this is just the name for the very specific standard. And we'll come back to this toward the end of the semester when we start using this. So does anyone want to guess what the decimal number is being used underneath the hood of a computer, so to speak, to represent this, which according to Apple is the most popular iOS emoji by far? I couldn't find a statistic for Android. I mean, actually, out of curiosity, how many people have recently sent this emoji? OK, so I guess the data holds out, proof by example. So anyone want to guess what the value is? Is it 1? Is it 65, 64? Is it 255, 256? Well, it turns out there's a hell of a lot of emoji these days. It is number 128,514. That is the decimal number that represents, what is it called? Smiling face with joy or crying face of joy, something like that. And there's a lot of other emojis, too. And they have different skin tones and the likes that just involves using more bits, more zeros and ones. So this is only to say that we have had in the past and we have had now in the future like a way of representing information, and we just evolved over time. And in fact, this is the pattern of bits. If you send a text message or an iMessage right now to someone with that emoji, you're not sending a picture per se. You're sending effectively this pattern of bits to their phone. And their phone, upon receiving that sequence of bits, realizes, oh, that sequence of bits represents the number 128,514. Let me display to the user the 128,514th emoji, if you will, that it knows how to display. So that's a bit of an exaggeration as to just how many there actually are. So we've got numbers that we can represent from binary, just zeros and ones and electricity. We've got letters and even things like emojis. But what else? Well, it's super common, of course, to use computers to send actual images or to look at photographs, take photographs, look at pictures on websites. And so here is just a single dot enlarged for the projector's sake. And we're going to call it a pixel. A pixel is just a single dot that has some color. How in a computer might I go about representing colors now? If you unwind the story, all we've got is like electricity coming out of the wall and switches to turn on and off. What could we do? How would you go about defining a color? Yeah?
You would have 3 different colors for RGB.
Yeah.
Then each one of them is like I guess that you send zeros and ones for red, zeros and ones for green, and zeros and ones for blue on each pixel.
Exactly. That's spot on. And there's actually different answers. There's different ways you can combine colors, but that's actually the most common one, RGB. If you've ever heard that acronym, it stands for red, green, blue. And if you also regress a little bit, if you think back to grade school or primary school or whenever we all played with like finger paints, right? Odds are you combine paints, which is a little different from combining waves of light, but you could, with different colors of paint, can you obviously make, well, as I recall, just like brown by just combining. Everything makes sort of brown by combining things. But if you think about colors being represented ultimately as some combination of red and green and blue, or RGB as you've proposed, you can imagine taking those colors and overlapping them and seeing what color it actually emerges. And so if we call this RGB, each of those colors uses 1 byte or 8 bits. So which is to say, you pick a number between 0 and 255, because again, that's how high we can count using a bit, or using a byte, which is 8 bits. So you use 8 bits to represent red, 8 bits to represent green, 8 bits to represent blue. So if you have the value 0, 0, 0, that's no red, no green, no blue. And it turns out that's how you represent black. It's just 0, 0, 0. But if you throw big values at red and green and blue, and this is where it diverges from the paint metaphor, then you have lots of red, lots of green, lots of blue. And it turns out that makes white. 255, 255, 255. And we'll come back to this because when we actually introduce web programming later in the semester, and you actually visually create web pages that have colors in them, the onus will be on you to decide, well, what color do I want to make my text or the background? And in the web, even though you can just say, make this page red or make this text blue, you can also specify more precisely, give me this much red, this much green, this much blue, and the browser will display exactly that for you. So if here we have 3 swatches of color, red, green, and blue, and we actually take 72 amount of red, 73 amount of green, 33 amount of blue. And then if you just kind of animate it in your mind's eye, overlapping all 3 of those colors, that is how we end up getting this murky shade of yellow here. But, underwhelming perhaps, but we can make a lot of other colors as well. But notice this, the resemblance of those values to something we saw earlier. What numbers did I just propose? Yeah, it's also high. And so somehow high is represented by computers as yellow. So it turns out context matters. Like if you're using a text messaging application or Microsoft Word or Google Docs or whatever, and your computer sees the pattern 72, 73, 33, odds are, because of that context and how that program is written, it's going to display to you HI exclamation point. But if you open up another program, Photoshop, for instance, if you've heard of it, even if you've never used it, it's like a photo editing program, well, odds are if that program sees the same pattern of bits 72, 73, 33, among others, it's going to say, oh, I should show the user not high, but rather 1 yellow pixel, probably among many others if you're indeed editing a photograph in it. So it's just context that actually matters. So it turns out you can see this if you just zoom in on some of the things we see here. And you might need to do this with special software because most phones won't let you zoom infinitely. But here is just a copy of that same laughing with joy emoji. And if I zoom in a little bit, still looks pretty good. If I zoom in a little bit more, starting to get a little pixelated, so to speak, a little blocky. And if I really punch in on it, now you can actually see what is going on with this image. It turns out that an image is just a whole bunch of dots or pixels, thousands of them, tens of thousands of them, depending how big the image is. And each of those pixels or dots just has some color associated with it. Each of those colors is 3 bytes or 24 bits. So just ballpark, if you had an image like this, how would you go about estimating how big the file is? If this is an emoji, and you know that every pixel is 24 bits, what kind of intuition would you use to estimate how big this emoji is on disk, so to speak? How big of a file it would be to actually send a copy of? Yeah. Oh, sir.
Multiplying the number of pixels with...
That's it. Multiply the number of pixels. I mean, literally, if I pointed at them, 1, 2, 3, 4, 5, 6, count them all up, all of those squares, and multiply by that value. Of course, we're zoomed in, so there's even more of them. but that's it. So all this stuff with which you might be sort of familiar on a day-to-day basis, it's actually not even all that complex so long as you start at so-called first principles and you understand from the ground floor up how you solve one problem and from there go about solving others. Now some of you with iPhones might be familiar with Animojis too, the sort of silly feature on iPhone X or your friend's phones that allows you to do Snapchat-style things on iPhones that actually creates animations or videos. And I will admit that Natalie and I have in the past spent far too much time over dinner like playing with Animojis, though it was only once and only once, but that footage is somewhere. But that results in video files, essentially. But what is a video? Whether in the context of Animojis or just movies on TV or movies on Netflix or movies in the theater, what is a video? Yeah, it's just a sequence of images flying past the screen quickly. If you've ever heard of 24 frames per second or 30 frames per second or FPS, doesn't matter if you haven't, that's all a movie is. And back in the day, they called them moving pictures because they were just pictures again and again and again flying in front of your face so quickly that it looks like animation. But each of the frames in a movie, and you can see it, if you just pause a movie or a video, you're seeing an image. And it might even be a little blurry because of compression and fancy techniques humans use these days to save space. But it's just an image, one of 24, one of 30 or so for that given second. So again, consider where we started the story, like electricity from the wall. Then we had zeros and ones that we can represent digitally, so to speak, as binary. Then we have letters of the alphabet, ASCII. From there, we can go to colors if we want. From colors, we get images. From images, we get movies. And all of that by simply deciding how to represent the inputs to some problem. And the outputs, presumably, come in that same format. Whatever the problem is you're solving, you're outputting an image, a video, a number, a string of text, that ultimately being how you solve a problem. So let me pause here, too, to see if there are any questions. All right, well, yeah, in the back.
How do you know where a string breaks? You can't just put a zero in like no string.
Where a string breaks?
Yeah, where a binary string, like where it ends, where a number ends, so instead of it being 72,000, or well, just a string of zeros and ones, it somewhere ends, right, like 8 bits.
Really good question. And I only alluded to this earlier. Humans do tend to use units of 8 bits. And so unlike schemes like Morse code, if you're familiar, where they're disparate lengths based on the character, in ASCII and in Unicode, you are always using 8 bits at a time, or maybe 16 or 24 or 32. So the boundaries are always at an 8-bit mark. The 9th bit onward represents the next byte. But there, too, it's context sensitive, because in some programs, you might interpret 4 bytes in a row, byte, 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 as 4 separate characters, or you might interpret it as a really big value for like a really big emoji, but it's totally context sensitive. The software, the program you're using, has to know how to interpret that data. And so when I mentioned we'll see things like UTF-8 and these fancy terms later in the semester, because when you're making web pages and you're writing software, you sometimes have to decide, I'm just going to get from my users a string of bits from the internet. How do I interpret it? So it depends. Other questions on inputs? Yeah?
Why use the binary system instead of the decimal system?
Oh, why use the binary system instead of the decimal system? Let me toss that back to someone for just someone's intuition. Why do you think? Like, why did we solve a problem in just a different way here? Yeah? Exactly. It just maps very conveniently to the physical world. It turns out that just having a switch that's on or off, or electricity that's flowing or not flowing, is just a very nice unit of measure. It's either doing something or not, and humans built things on top of that. There are systems like ternary, where you actually have 3 states, sort of one here, and one here. But it turns out that can be a little more error prone, especially if there's a bit of noise. And if you do take a class in like electrical engineering, or if you've used a battery in the human world recently, you know about things like voltages. Well, generally, voltage is also a very noisy medium, and so you roughly want your 9-volt battery to be close to 9 volts or close to 0 volts when it's dead. You don't really want it in the middle, because then your hardware is not going to perform correctly. So it's just convenient, really. Yeah?
What happens if you want to write a message saying, hi, exclamation mark, I'm 65 years old with 6 and 5, right? Then how does it know within that framework when the sun is?
A really good question. If you want to send a message that mixes letters and numbers, it turns out that you are technically sending only characters, as we're going to start calling them in a couple of weeks. So this is just a website I knew the URL of, ASCIIchart.com. It's looked like this for 20 years, and it's provided courtesy of Appropriate Solutions, Inc. for some reason. But this is just a mapping of decimal numbers to the ASCII letters that they accord to. And if you look at the chart, you'll see in the middle, 65 is A, 66 is B. But if you look farther to the left, how would you actually represent in a text message or whatnot as you propose, hi, I am 5 years old? Well, how do you represent that 6? As the pattern 54. And 65 is actually the pattern 53. So in the context of sending text, even if the symbols you're sending look like human numbers, they are still represented in this same system called ASCII. Great question. Any others? Yeah, over here.
How would you do a yellow letter?
How would you do
A yellow letter. Like a,
Oh, really good question. How would you implement a yellow letter? OK, a lot of combinations here. So I hate to give a simplistic answer, but it totally depends on the piece of software. So a program, such as the ones you will all be writing before long, you would have to decide, well, if I want to allow a user to colorize all of the letters in his or her message, well, I minimally need to use 8 bits for every letter he or she is sending. But to represent the color, I might need 8 plus 8. I might need 24 more bits to represent the color of the letter the human is sending. So you know what? I, this programmer, am just going to use 32 bits, 8 for the letter, 24 for the color, to represent every letter that I'm sending in this message. But you could do it any number of other ways. It's totally up to the designer of the software. All right, so from there, if we now stipulate we have a way of representing information, or more generally just inputs to problems and the outputs to those problems, this course, and computer science more fundamentally, is really about what's in between those two. The thought processes, the instructions, the so-called algorithms, step-by-step instructions for solving problems that fits here inside this proverbial black box. So what might be an algorithm that we want to solve something with? Well, consider something like this. It's a little old school these days, but this is or was a phone book and has a whole bunch of names alphabetically from left to right, and it has a whole bunch of phone numbers in it. And even though this is kind of an old school technology, honestly, if you think about your own iPhone or Android phone or whatnot, and you open up the contacts application, odds are those contacts are sorted from top to bottom, A to Z, either by first name or last name. So it's pretty much just the digital version of this. So if we can solve this physical problem, we could then apply that same logic as a programmer to solving a problem in an actual Android phone or iPhone or just address book more generally. So if I want to solve a problem, and here's the input represented on paper as numbers and names, alphabetically from left to right, and I want to find someone like Mike Smith, and the whole book is alphabetized by last name, maybe I'll start at the beginning. And I'll look at the first page and look for Mike Smith. Not there. So I keep going. And I keep going. And this is a step-by-step process. Literally, page by page, I'm looking, should be looking, for Mike Smith. And when I find him, I'll eventually call him. This process, this algorithm, is it correct? Yeah, it's correct, because if Mike's here, I will find him. And I think intuitively we'd all agree, if the problem is to find Mike Smith, this algorithm, though slow, is correct because it will eventually find him. But it's slow. It's inefficient. All right, so from grade school, I also remember counting by 2. So 2, 4, 6, 8, 10, 12. All right, I'm going through faster, and I'm being a little sloppy, to be fair. But is this algorithm more efficient? Yeah, I mean, it's literally twice as fast. But is it correct? OK, why not? Yeah, I could get unlucky, and once I get to the S's, oh, damn it, just by bad coincidence, Mike gets sandwiched between 2 pages. So the algorithm is incorrect, but do I have to just throw it away altogether? Can I fix this? What could you, the human, do? If you're flying through and oh, damn it, I passed Mike Smith, do you just give up? Obviously not. You just double back, right? So there is a fix. So I would argue this algorithm's twice as fast minus 1 step. Because if I go ever so slightly too far to hit the T section, for instance, or SN instead of SM, then I might have to double back 1 page. And that's not bad, right? If this is 1,000 pages, OK, doubling back by 1 page, really just a drop in the bucket. But none of us are going to solve this problem in either of those ways, right? If you're going to solve this problem, what are you going to do these days? Yeah, just go roughly to the middle or the S's if it's not obviously labeled on the outside. And OK, I look down, it's roughly in the middle. I'm in the M section. And I know alphabetically Mike is to the left, Mike Smith. And so what do I know about this input now? Where is Mike? Yeah, it's on the right, Mike Smith. Yeah, so on your left. So Smith over here. And now just to be dramatic, we can, damn it, tear the problem, thank you, in half. We can tear the problem in half, like throw half of the problem away, and what we're left with really is the same problem. But it's the same problem in the sense that I can use the same logic, the same algorithm, but I've taken a 50% byte out of the problem. And that was way bigger because the first algorithm took 1 byte, the second algorithm took 2 bytes. This time it took like 500 bytes out of the problem all at once in one instant. And now I go do the same thing, roughly in the middle. Darn, I went a little too far. Now I'm in the t section. But again, I can apply the same, much easier now, logic, throw that quarter of the problem away, and be left with like 250 pages. And I can repeat and repeat and repeat until hopefully logically I'm left with, let's just say, the injury law page, let us win and fight for you, that is not Mike Smith, but it is in fact 1 page. And so how quickly did I actually get there? Well, if you imagine starting with like 1,000 pages, the first algorithm might take 1,000 steps at worst. Like if Mike's all the way at the end, or maybe S isn't in the Z section. So let's say that first one was going to take like 750 steps, give or take. Now the second approach would take maybe 300 steps, 325 steps or whatever, because I'm going twice as fast. But this algorithm, where I started with 1,000 pages and went from 1,000 not to 999, and not from 1,000 to 998. I went from 1,000 to 500 to 250 to 125 to 60-ish to 30-ish to 15 to 7 to 3 to 2 to 1. And I'm just kind of rounding to clean it up. To 1. I mean, that was pretty darn fast. And in fact, if we did that perfectly arithmetically correctly, how many times can you divide roughly 1,000 by 2 by 2 by 2? It's actually only about 10 times. So with just 10 dramatic tears of the page, could I find Mike Smith, as opposed to it taking maybe 1,000 steps, or maybe even taking 500 steps, I whittled it down to 10 by just leveraging the intuition, dare say, that all of us are generally familiar with already. Now, as an academic class, let's try to apply some thought process to just what this performance looks like and see if that recurs down the road. But first, let's express this a little more precisely. So pseudocode, I claim, is just a way of programming using English. There's no formal definition of this. You just use succinct, clear English that gets your point across, and you might generally number your steps just so that you can refer to it verbally. So here might be the pseudocode for representing that algorithm. If I wanted to repeat it or feed it to like a robot to implement as well. Pick up the phone book, open to the middle of the phone book, look at names, and then I have to start making some decisions. If Smith is among names, call Mike. That's a success. That's the output. Else, if Smith is earlier in the book, open to the middle of the left half of the book, as I did, and then go back to step 2, focusing on the middle of the left half at that point. You don't have to technically tear it. Else, if Smith is later in the book, do the same thing but to the right. Else, and the fourth thing is important, if he's just not there at all, and you get down to 1 page and he's just not on it, you have to do something. You can't just hang or sort of do the spinning beach ball or hourglass like Mac OS or Windows might do if a programmer didn't anticipate a fourth scenario. That fourth scenario is he's just not there, so you should give up. So let's call out some fundamental building blocks here. Everything highlighted in yellow at the moment look to be verbs in English. They're actions. And moving forward, we're going to start calling these things functions, functionality that a human might have, or eventually that a computer might perform on that human's behalf. If we highlight these next words in yellows, if, else, those are going to be called conditions or branches, the proverbial fork in the road, if you will. You can call it any number of things. It's just a decision point on which you need to make a judgment call. And then there's these, the actual questions you're answering in order to decide to go left, so to speak, or right, or down the middle road. And those questions might be, is Smith among names? Is Smith earlier? Is Smith later in the book? Those, more fancifully, are going to be called Boolean expressions after someone named Boole. But they're just questions that have yes, no, or true, false, or heck, 1 or 0 answers, right? It doesn't really what we call any of these terms. We can even distill them down to 1s and 0s, and that's great because computers can do exactly that. Lastly, something here highlighted in yellow, go back to step 2. That might just be a loop. It's some kind of cycle that we're inducing. And indeed, that's going to be another construct that we have in programming, not using English or pseudocode, but rather using more traditional languages. But before we do that, let me propose this. How do we think about just how fast or slow that algorithm was? Well, we don't actually need to do any kind of actual strong measurements. or actually precise measurements, but let me just propose a relationship. So here's a general graph. Let's actually call this like time in some unit of measure, seconds or whatever. This is number of pages, or more generally, let's instead of calling this pages, let's just genericize it as the size of the problem. So if this chart represents along the horizontal axis how many pages are in a phone book, and the vertical axis represents how much time it takes to find Mike Smith or anyone else, the performance of the problem, what shape did the first algorithm have? Took me 1,000 steps in the worst case, and what's the relationship between the length of the phone book and the amount of time? Yeah, it's linear. It's a straight line. Why is that? Well, a handy way of thinking about it, I think, is if like the phone book company, Verizon or whoever, adds one more page to the phone book next year because a bunch of new families move into town, well, that's going to add a page to the phone book. And suppose you're looking for a family whose last name starts with Z. They're all the way at the end. In that first algorithm, you might have to turn 1,001 pages to get to them. So one more page, one more second. And so the relationship is a straight line. One more page, one more second. One more page, one more second, and you get a straight line. The second algorithm, where I was flying through the phone book 2 pages at a time, what's the shape of that algorithm going to look like? Yeah, but steeper, I heard. Yeah, so steeper at least, or lower in the way I'm drawing it here. For instance, if this line is straight up this way, the other algorithm is going to be half as high. Now, how do you think about that? Well, for instance, if this is the number of pages in the phone book, the first algorithm might take this many seconds, whatever that is. The other algorithm should take half as long. So I just eyeballed it. Hopefully that point is roughly half as tall as the other point. And that relationship holds no matter how far out you get. And this one's a little less intuitive, but that third and final, dare say intuitive algorithm, dividing and conquering the phone book in half and half and half, has a fundamentally different shape that's actually curved, that doesn't ever flatten out, but it almost looks like it is because it starts to grow, so to speak, starts to rise so terribly slowly as the problem gets really and really big. How do you think about that intuitively? Well, if Verizon next year consolidates 2 towns, like New Haven and another town over, just for whatever bureaucratic reasons, the phone book might go from 1,000 pages to 2,000 pages overnight. But how many steps is that third algorithm actually going to take? Just one additional step. So even if this is 1,000 pages and this is 2,000 pages, it just barely increases, maybe by 1 second or 1 additional page turn. And that holds true the farther and farther out you go. And this is only to say that even if computer science doesn't necessarily feel like something with which you're all that familiar or necessarily going to be comfortable, it really is about just harnessing some of this intuition and these heuristics that we take for granted, but kind of formalizing them so that you can really and powerfully solve problems that you're actually interested in, and not just some of these smaller examples like counting and representing numbers. Like the intuition isn't all that far away. But of course, with this phone book, or with the contacts in your Android phone or your iPhone, they're sorted already. Right? I made a pretty serious assumption that that phone book was sorted. And in fact, that's perhaps not necessarily fair. Could we ask for one volunteer to come on up? He or she's got to be comfortable appearing on camera, but you don't have to say too much. Yeah, what's your name?
Katarina.
Katarina, come on up. Nice to meet you. Yep, right this way is fine. All right, David, nice to meet you. So behind door number 1 here, we have a whole bunch of pieces of paper. And I would like you, there's no prize at the end of this, sadly, but I would like you to find for us the number 50. Nope, that's the number 8.
Are they in order?
That's the number 42. That's the number 4. 50. All right, applause for Katarina if we could. OK, just wait 1 sec. So why did you ask me if they were in order?
That way I knew if it would be to the right or the left.
Yeah, and so indeed they weren't. These numbers are all pretty random in this case. So she actually did as well as anyone could do at the board, and you could have even gotten lucky, but not by any kind of formal process or algorithm. You just took 3, 4 steps that time because you had no other information to go on. But if we instead do give you that assumption, now dramatically behind door number 2, we have 7 more pieces of paper, but I do tell you this time they're sorted from small to large, like a phone book, like a contacts in a phone. Where are you instinctively going to start, probably?
Probably in the middle.
All right, so start in the middle, sure, because you don't know how small or how big the numbers get, but find me the number 50 with this set of data. That's not the That's a bug, if you will. Okay, 16, not 50, but what do you now know?
That this is to the right.
Exactly. We don't have to even bother looking at any of these numbers. So find me 50.
So I'm going to look.
In the middle of the right half, nope, still 42. But where are you going to go next?
The only way. So
And why that way and not this one?
because this is going to be smaller.
Good, because 42 is smaller than 50. So excellent. A round of congratulations. So it seems to be a very powerful thing if you're allowed to assume from the get-go that your data is sorted. Well, that's great. But someone had to do that sorting, right? Verizon sorted the phone book, or Apple or Google sorted your contacts so that you can then benefit by looking up Mike Smith quickly, or all of us are familiar with like autocomplete these days where you just start typing characters. It turns out that phone that you're using when you're searching for someone is probably using this same algorithm that Katerina did. It looks roughly in the middle of your contacts. And then if you're looking for Smith in your phone is going to look only at the contacts below or only at the contacts above so that it can find things much more quickly for you, logarithmically, so to speak, but more on that down the road. But if we need to actually sort the humans, it kind of invites the question, well, that's all fine and good if searching is fast, but how fast is sorting? Right? How did I, before class, or Colton, who lent a hand before class, sort those numbers? And indeed, just to prove that this was not fixed, these numbers, same numbers it turns out, but they are in fact sorted. But they didn't start that way. So actually, why don't we do this? Rather than answer it in the abstract, can we get 8 volunteers this time? OK, 1, come on down. 2, 3, 4, 5, 6, 7. No one from this side? Really? No, OK, 8. Come on down. All right. And if you could just greet Colton over there. He's going to hand you a prop. And go ahead and take a seat wherever you would like. OK, take a seat wherever. All right. And just to make this a little more personal, should we just fly through the line? Do you want to just say your name and your college and pass it on?
I'm Victoria, and I'm in Trumbull.
Victoria?
I'm Will. I'm in Poly Murray.
Elena, I'm in Hopper.
Andy Berkeley.
Adam Morris.
Tiger Pearson.
I'm Valentina. I'm at the School of Management.
I'm also Victoria. I'm in Ben Franklin.
Excellent. Glad to have you all up here. OK, so key step now, if you could go put on what you have been given. All right. So hopefully you did not sort yourselves. Good, because then we'd have very little to talk about. So I see a 7, an 8, a 4, a 3, a 5, a 2, a 6, and 1 all the way at the end. So this invites a question. How do we go about sorting these folks? And now notice it's actually deliberate that we gave them chairs, because it turns out in a computer you have stuff called memory, and more on that before long. But memory is in specific physical places, just like our humans are in specific physical places. And for now, we're going to have each of them representing a number, and numbers might take 8 bits or more. So each of them represents 1 or more bytes, but in a very specific location. So I see that you're clearly out of order. So why are they out of order? What does it mean for these humans to be out of order? Like, identify the problem, not just intuitively, but precisely. Yeah, sure.
We randomly sat down.
You randomly sat down. OK, what does random mean, though?
That means you're not actually sorting as you go. Like, you couldn't search and sort, but we just sat down.
OK, you just sat down, so you're not sorted. And just could you or someone clarify what would it mean to be sorted? Yeah.
Like, my location doesn't tell you anything relative to me. So, like, if we were actually in order, you'd know that anything to the right of me is bigger than me.
Good.
Anything.
So what I'm hearing here is rather than use words with which we're already familiar, like random or such or sorted, now you've given us a more formal definition. Everyone to your left should be smaller, presumably, and everyone to your right should be larger. And because we have a 3 to your left and a 2 to your right, it's not sorted because the 2 should obviously be somewhere to your left. So let's just start at the beginning here. So we see 7 and 8. Are they in order? Are 7 and 8 in order?
On which way we go, yes.
Yeah, if we're going to, the goal is to be clear, good qualification from smallest to largest, as before. So 7 and 8 are in order. I still have some problems ahead of me, but they're in order, and there's really no work to be done here. What about 8 and 4? Are they in order? No. So would it improve the situation if we had them kindly swap seats? OK, so yeah, if you wouldn't mind. 4 and 8. All right. And now let me keep going ahead. 8 and 3, are they out of order? Yeah, so if you wouldn't mind as well. And let's see, number 8 and 5, if you wouldn't mind yet again. I'm sorry, you're going to be doing this frequently. 8 and 2. How about 8 and 6? And sure, how about 8 and 1? OK, thank you. So problem solved, right? No, but it is better. In what sense is the problem better off now? Yeah, 8 is where she should be all the way at the end. So in some sense, I can kind of sort of ignore, if we could here, number 8, because that problem is solved. So the problem has gotten smaller. It didn't get halved, per se. This problem is not as easily solved as finding Mike Smith in a sorted phone book, but we did solve or chip away at this problem. And honestly, if we repeat this process, I think it's going to kind of play itself out, right? Because 7 and 4, if you wouldn't mind swapping. And then 7 and 3, if you wouldn't mind swapping. And 7 and 5, 7 and 2, 7 and 6, 7 and 1. Problem's getting better. But notice, I'm using the same algorithm, right? I'm just looking at two people side by side. And if they're out of order, swap them. And it's taking me some time. I got to do it again. But notice, I don't have to go all the way back. I can kind of focus now, if you will, only on these 6 problems. So 4 and 3, if you could swap. 4 and 5. Whoa. That was a bug. OK, you're good. 4 and 5. OK, but 5 and 2, out of order. 5 and 6, nope. OK, 6 and 1. 6 and 1, out of order. And now 6 is in place. And let's go ahead and just kind of fast forward, just so we can get the dramatic reveal. What should you look like if we just expedite this algorithm in the end? OK, correct. But what was that algorithm? Right? And so there's a difference. Like, all of us have a nice intuition for solving the problem. But if you really sat down and tried to explain to like your younger sibling who's really young cognitively and needs to be told exactly what to do, or you tell a robot these days exactly what it needs to do, you really need to distill this intuition into something a little more formal. And that was just one way. But it's probably not the only way. In fact, could we do one thing? Could you just randomize yourself? And I'm not technically giving you a definition of that, but odds are we'll just kind of make a mess of the problem, and we somehow have an intuition for that too. But just to point out that there's not one solution to a problem, and we won't even touch on all of them today. You know, there's I claim there's an easier way, or there's at least another way to solve this problem. You know what? I could just look through the numbers. My goal being smallest to largest. Let me just find the smallest element and not walk back and forth like I was, swapping things, which felt like it was messy and it worked out, but it just felt like a lot of labor. So, all right, 6 is pretty small so far. 7, you're bigger than that, so that's not, 5 is better. 2 is really good. 3, 2, 1. OK, I found the smallest, I should double check. Yep, I found the smallest element. So if you wouldn't mind standing up, where does she belong? Yeah, all the way over, could you? So I can just move my data around, and if number 1 wouldn't mind coming here. Now, I've coincidentally made part of the problem better by moving a bigger number up, but I really just needed to make room. But I could have done that differently. And actually, would you mind swapping back for just a second? I don't have to just summarily evict number 6 to make room. What else could we have done that might have been a little more polite? Or if you imagine being in the theater or movie. Yeah, I saw this. So if number 1, could you sit up? And then if you guys wouldn't mind, could you just kind of scoot down? This would be another way to do. Which of those ways is better? The first way or the second way? You say first. Why?
Uses less memory.
Uses less memory. Well, I still see 8 people and 8 seats. So I don't think I've added any seats or people.
Number of operations is less.
Operations. The number of operations would seem to be less, because even though you're independent beings, there was just more physical effort going on. And frankly, I think my first instinct of just swapping 1 and 8 was just a little more efficient. But it's no more correct than this approach. So again, there's this tension between correctness, perhaps, and efficiency, such that by spending to gain a bit more efficiency, you just have to think a little harder about the problem and try to avoid doing work. And so that's kind of the great irony. By pouring more time into writing your code or writing your algorithm, can you, over the long run, really solve problems and save time significantly? So if we could, a round of applause here for our volunteers. If you want to go off that way. You're welcome to keep the shirts. We just need the numbers back. And so where are we going to go from here? So again, we started the story by talking about data and representation, just zeros and ones, and all of a sudden we're solving problems algorithmically. It turns out those algorithms have fancy names. The first one most people call bubble sort. Bubble sort in the sense that the big numbers kind of sort of bubble up from left to right, making their way to a position, their correct position. The other one's called selection sort typically, because what I was doing was selecting the smallest element. And even though we didn't finish that story, because it would get pretty tedious pretty quickly, the next step would have been, let me find the number 2 and put him or her in place. Then let me find 3, put it in place, and so forth, iteratively, again and again selecting the next smallest element. And thus far, we've done this very physically. We've done this very verbally, very much in pseudocode, if you will, like the text here on the board. And so this class ultimately is going to be about expressing these same ideas, but using languages. Languages called Scratch, which we'll soon see, which is actually a graphical programming language via which you program by dragging and dropping things that look like puzzle pieces that you can only lock together and interconnect and make things like a cat move up, down, left, right, or meow on the screen if it makes logical sense to do so. But then very quickly, are we going to transition to a more traditional but more textual language called C, where you actually type code that is just English-like syntax that's even more succinct and more terse than my pseudocode before, but it has a formal definition, and it's way smaller than English. So in some sense, even though the logic might take time to get comfortable with, and remembering the syntax may take time, there's far fewer words and symbols in a language like C than there is in English or whatever your native language is. So realize that even though it might look like the proverbial Greek to you at first, it will get more familiar quite quickly. From there, we'll introduce languages like Python, with which you might be familiar, at least in name, very much in vogue and allows you to solve problems in the data sciences and medical sciences and arts and humanities. If you have data that you want to manipulate or images that you want to analyze or text that you want to search, we'll introduce JavaScript, a language that's used on browsers typically these days to actually make more interactive user interfaces and make better experiences for users and help him or her actually navigate data or actually access information or content that you want to provide to them. SQL or SQL, this is a database language. Once you've got some really juicy data or lots of users, lots of customers, or lots of medical records that you want to search, turns out you can use another language called SQL to actually search that data and store it more efficiently. And so rather than be a course about just one language or one way of solving problems, we give you this whole arsenal via which you can actually solve problems using the best tool ultimately for the job. We'll start by writing the simplest of programs next time, whereby you'll literally drag a couple of puzzle pieces, an orange one and a purple one, they'll lock together, you'll click play, and the cat will meow. And we'll very quickly do more. And a week after, will you be doing something very similar in spirit, but much more powerfully. And ironically, we're going to take away the menus and the buttons and all the graphical components with which you're very familiar on Macs and PCs, expose you to things like a terminal window, so to speak, a black and white window that's just text, but at which you can actually start expressing yourself more succinctly, more powerfully. It's just going to be a bit of a learning curve. And so you get comfortable with what otherwise is an unfamiliar space. In just a moment, we'll adjourn outside where the TAs and staff have a wonderful assortment of cake for you, as is our tradition, so that you can say hello and ask any questions of us. There's no homework this week until next, but we thought we would end with something more visual. I'm going to go ahead and dim the lights for our final 60 seconds here, because even though we focused today on ideas and on problem solving, it turns out that as Natalie and Benedict introduced, there's a whole team around you and a whole academic and social support structure that we've captured here thanks to last year's students in both New Haven and Cambridge.
What about us? What about us? We are searchlights we can see in the dark. We are rockets pointed up at the start. We are billions of beautiful hearts. And you sold us down the river too far. What about us? What about all the times you said you had the answers? What about us? What about all the broken happy ever after? What about us? What about all the plans that ended in disaster? What
right, that's it for CS50. We'll see you next week.